amazing. All right. Um, well, yeah, thanks for having me. Um, Giovanni, I'm a founder and CTO at Sysdig. Um, I'm here to Falco, so we'll cover, like native security, Kubernetes security, and in particular, for point of view of runtime security, which is what Falco specializes in. Um, I have like the ballpark of here feels like 90 minutes is time to do a monologue. So we'll see how long it lasts, but let's make it interactive. It's a meetup here. We all got to know each other. So if you have questions or a comment, feel free, to make this conversational. So hopefully it's going to be less boring. Um, Start with a little bit maybe of history to provide you context. Well, actually, Sysdig, which is the company I'm currently the CTO of, is my second company. My first company was called Case Technologies and was the company behind open source network analyzer called Wireshark. I actually started working on Wireshark by building the capture library for Windows, which was called WinPickup. It's what you use essentially when you run Wireshark on Windows. And started working on that when I was in school in Italy. From my accent, that I'm coming from Italy, and actually I worked on that for a bit while I was here in New Zealand. And I was still a student, a PhD student. I was invited by a company in Hamilton, actually called them Days, to do a little bit of work on high-speed packet capture. And it's also the time when I worked on the pickup ng format, So if you're doing pickup files, uh, when you're doing Wireshark, one piece of tree is that the format was actually defined here in New Zealand while I was doing my internship. I started the company in 2006. That's when Ethereal was renamed into Wireshark. Essentially, what happened is Gerald, the original creator of Ethereal, and I started the company together. But the Ethereal, mark and website domain and so on, were owned by his prior employer. He was working for a little either in Kansas City in the United States. And so we went to this guy and we tried to purchase his assets, but I was out of school and Gerald was in first job. So and no one has venture capital money at that point, So we just forked the project, gave it a new name. We picked Wireshark as a name. And we started the Wireshark website. We told the community, it's not Ethereal anymore. You need to go to the Wireshark website. And the community said, fine. And that's how the Wireshark name was born in 2006. What we were doing at the point was working on packet capture and essentially using these insights coming from network packets for a bunch of stuff. In building, reconstructing the behavior of applications. If you're able to see the packets and dissect the protocols, that are carried in these packets, then you can actually understand what applications, points, users are doing, and you can use this information for visibility purposes, for troubleshooting, for monitoring, and also, of course, for security. We got acquired in 2010 by a company called Riverbed, and both Gerald and I went work for this company. And while we were there, clearly the world was the world of IT was starting a big generational transition. A little us provider in San Francisco called Dot Cloud was renamed the container revolution was born. Uh, Kubernetes, the first version of Kubernetes was released, like in 2014, if I remember well. So there was all of this new excitement, around doing computing, but same time it was pretty clear that it was changing architecture and changing it in a way that doing things in the old way was not feasible and effective anymore. What I mean is, for example, from the point of view of visibility and data collection and security, um, how do you capture the packets when you're running EC2 instances or whatever, or Amazon or Microsoft instances in Azure and so on, Microsoft or Amazon on the network. You cannot, you don't have the span port of the router anymore to get the packets and so on. At the same time, there are people that pack hundreds of containers. We have customers at Sysdig that have 300, 400, 500 containers in 96 core machines. There's so much that is going on that if you're sitting on the network, you're missing all of this stuff, right? So I remember that when I was in case to say packets never lie, because if you're on a physical, data center and you can sit on the span port of the router at the top of the rack, you can see everything. Nothing can escape you, especially if you can actually dissect the packets and they're not encrypted. But in the new world of cloud, packets actually can lie, mostly because there's stuff that you cannot see, and there's stuff that can escape you. So, around 2013, 2014, I decided to leave Riverbed and start a new adventure with Sysdig. And the goal at the beginning was, just at the architectural level, actually, what is the right way to approach security instrumentation, in particular for runtime security, if you can design it from a blank sheet of paper for the world of cloud and containers and microservices and Kubernetes and so on. Company started, open source is what we knew uh, how to do stuff. And so the company was started on background, and we decided to release from essentially day one all of the software that we are building, including the key part that have to do with like instrumentation and modules and all of this kind of stuff, which is interesting because we'll talk a little bit about that later, but the approach that we created during those years for like instrumentation is essentially what the industry is standardized around. So we sort of invented runtime security for Kubernetes. And the first thing that we released is an open source tool that play with it. I recommend you do. It's a lot of fun. It's essentially TCP dump for system calls. Talk a little bit about system calls for a second. And the other tool that we released in 2016 released is Falco. And Falco comes very much from our background in packets. So the reason why I did this story about, like the packets background is because really the instrumentation that we built for Sysdig initially and for Falco a couple of years later really can be seen a little bit like applying all the concepts, architectures, workflows around packets, but instead of using packets, essentially what we use in Sysdig and Falco and in our commercial products is system calls. System call is they are the interface between software and the operating system that runs the software. So opening or closing a file generates a system call. Reading and writing on a file, machine network connections, or receiving as a server network connections, system calls, sending and receiving data on the network, executing commands, doing inter-process communication. All of this stuff is system calls. So they are this very granular, essentially, data set. And it is a little bit like Wireshark for system calls. And Falco is a little bit like the system call version of the network intrusion detection tools that are used in traditional security in the data center. Tools like Snort or SourceFire or Suricata and so on. We were heavily inspired. You never invent something new, but especially for this, what we did was just, okay, what worked in the prior generation and what did users like, in the prior generation, and let's try to create, like a data source and a data collection mechanism that would fit to the new world and be effective for the new world. Let me stop for a second. Let's keep going. Okay, we've done a little bit of history. Now let's do a little bit of like top down, and in general, like framework for runtime security. What in cloud native is defined as runtime security, and a little bit of motivation for that. First of all, yeah, these are expensive. This is a statistic from IBM. Every breach on average globally costs like over 4 millions essentially. And of course, the longer it takes to detect and block the breach, and the more expensive it is. So in general, there's a need in the industry able to intercept this kind of stuff and address it quickly. One thing today, I was part of a panel at the security conference that was at the Hilton, and one thing that I mentioned is a year that is coming from SysDig threat research team. So our threat research team was able to intercept a cloud-based attack, cloud infrastructure, in one of our customers' infrastructure. It was essentially an attack that advantage of vulnerability to the instances, leverage the local privileges to do reconnaissance, found like a Terraform potentials somewhere in storage, we're able to leverage them to mining, exfiltrate data laterally, and expand more inside the infrastructure. These 10 seconds. Stuff now is automated, scripted, and guys are doing DevOps too. So, the classic solution, in the data center was build a very thick wall around your infrastructure and your data, build a very, very small door for the wall, right? And that was like our concept. You have your perimeter, you have all of your stuff inside your perimeter, and then you try to, protect the entry and exit point of this perimeter as well as you can with different layers of security and like network security and firewalls and all this kind of stuff. Picture, the problem is that modern world is more like an amusement park rather than a castle, right? Our infrastructure, cloud, we have users, normally, global workforces that access our infrastructure and our code and our data from all over the world with different credentials. We have the developers, we have the ops, we have IT people, we have consultants, and so on. People need to operate freely, and go back and forth. So, there's no real narrow entry anymore. There's many entries from different parts, and you want people to be able to really fluidly operate and go from one place to the other place. Plus, in addition to that, of course, you have users. Every software company is a global company. Every software company has users from all over the world, right? And every software company has their apps, their websites, their applications, the internal and external, and different environments, and production, and dev environments, and all this kind of stuff. Our point of view when we started working on Falco is that a better metaphor to solve this problem rather than the, like firewall and the little door that is very heavily guarded is the security camera. So what do you do in an amusement park? What do you do in a city like Auckland, where you have people that need to circulate freely, but you still need to guarantee security? What you do is you try to monitor, try to get visibility that is as detailed and as granular as possible. Try to do that in a way that is ideally in real time. And then, you collect this data from as many locations and sources as you can, and you bring it to a centralized place, and you use this data for your reaction to then, take different types of actions depending on what the data that you're seeing is. It can be lightweight action or can be dramatic action depending on what your network of security camera, right? Falco is a little bit the security camera for cloud-based software infrastructures. It's at its heart a runtime security engine, and it merely to security cameras in a city that can be in different places and different locations. Falco tries to do the same. So it has multiple data sources. First of all, the kernel of the operating system. We'll talk a little bit about that, but this is where system calls play a role, but also cloud trails. So, logs that are coming from the different cloud providers. Falco is integrated with all of the ones, and also application logs, all of the applications that are really an integral part of a modern cloud native application architecture, Okta, and all of this kind of stuff. Falco tries to approach this from the runtime security point of view. So the goal of Falco, for example, when integrated with GitHub, is not really maybe like doing code security like companies like Snyk, for example, do, but it's more like intercepting in real time user behavior and being able to quickly collect this information, understand it, have policies on top of it, and potentially correlate with other information. For example, an attack that is happening on the host. And Falco is a cloud native computing foundation project. So we contributed Falco. I started working on Falco originally with a little team at SysDig in 2016. We donated it to the CNCF in 2018. And as we speak, the public comment period for graduation opened days ago. So we are now in process, hopefully, to graduate CNCF graduated project. It's very important for us because the graduated projects at the CNCF are native Prometheus. So it's sort of that's the definition of modern stack, and Falco wants to be essentially runtime security part of the modern stack. That's why we decided to contribute it to CNCF. At its core, Falco relatively simple. So you define policies by writing rules. Falco evaluates these policies and gives you output. A shell was spawned in one of your containers, or a cat was executed in a container that allows remote execution. These are two examples of things that Falco can detect. The most basic way to do it is you just run Falco as a command, on your Linux box, and it's able to start detecting this kind of stuff, and it will just print this kind of output on standard output. So you get like an engine that is able to do this kind of detections and just prints them on the screen. Of course, that's not the way you deploy it in production, but still, the Falco agent at its core can work on an arbitrary machine. At its core, the sensor is two inputs. The rules comes normally through rule files that are typically, in a typical deployment of Falco, in some kind of centralized way, typically, using like DevOps kind of approaches. And then events. Events are what is to Falco as if rules are evaluated for each event that is coming in. And if the event matches the rule, you get an alert. Example is what I gave you before. If there's a rule for a shell being spawned in a container, and that evaluates essentially the execution of possible programs, including Bash and SH and TCSH and so on. And if one of these is executed, essentially the rule trigger and the triggers, and you get an event. We'll talk a little bit more in depth about rules in a couple of minutes. Of course, one sensor is not very useful. So what you normally do is deploy many sensors that can fetch different frequencies, each of them. Sometimes, some people a very big company laptops like these has hundreds of thousands of Falco sensors in there. So to give you magnitude order, you can have small deployments, you can have one sensor, but there's also deployments of Falco that are in the high hundreds of thousands of sensors or more exploding a little bit the architecture of the sensor. There are typically three important components that are like embedded in the sensor. One is what we call Falco libs, so the libraries that are like the data collection of the sensor. And the libraries can use stuff like kernel modules or eBPF probes to collect system calls, namely from the kernel of the machine where the engine is running. Or the Falco libs have a plugin architecture support, and plugins can include CloudTrail, Okta, your logs, you name it, and this is extensible, and there's also stuff that is, people build just like for fun, like with a plugin or stuff like that.
Yeah, and this is a really good point. Falco is very extensible, and it's got a plugin architecture that the community can contribute to, and it's very, very powerful. And so, yeah, I just wanted to mention that it's a very extendable. So if you want to write your own plugins, it's cool too. So yeah.
In theory, you could write a Falco plugin. I don't know, toaster as an API to get an alert when your toast is ready. The Falco libs act as a unifying layer essentially for all of these different inputs, and like a normalizing, so that then the rule engine operates on data that is relatively standardized in format, and you can express, using the same rule syntax, policies that range from, I want to detect if a binary file was modified in one of my machines, or if data was exfiltrated from a cloud storage repository, or my toast is ready. Essentially, you can write a policy that is based on a common syntax. And typically, the rule engine just emits basic words. They can be just text or JSON. They can be formatted in 3 or 4 different ways. And then there's called Falco Sidekick, which is a project, a Go project that is designed to essentially sit near Falco and collect these raw events that are coming from Falco and integrate these with, you name it, whatever you want in your infrastructure. So Falco Sidekick is essentially the connector between the Falco rule engine and tools, email, Slack, third-party tools, Kafka, whatever you want, essentially. And that makes it possible to create, like, for example, response engines. There's 2 or 3 open source response engines that are integrated with Falco Sidekick. And for example, based on the output that is coming from the Falco sensors, allows you to take some actions, for example, kill the container, quarantine the machine, block the network connection, this kind of stuff. Right? Good questions?
So far, what should of the way you describe it, Falco? I don't see necessarily the need of running that inside a container. So could we do that in VMs?
Absolutely. That is exactly what I'm going to talk about next. So thank you for the question.
Right. Thank you for the questions. We do have minutes for people who actually ask questions.
Wow.
That's when you're done.
Yes.
Like HDRs or modern sort of tech. I mean,
Yeah,
you can feed to like Seams or
exactly. So in 15 minutes, I'm going to cover that a little bit more in depth, because from one point of view, you can see Falco as a tool that fits data into an XDR, for example. XDR, I don't know if everybody's familiar, but there are these tools. It is sort of an evolution of a logging collector like Splunk and so on, but with more focus on security and security signals. So Falco can be the input for the XDR, but another important use case for Falco is just processing, maybe logs that are coming from the cloud that tend to be extremely verbose, and being able to do it in a streaming fashion, actually more effective and much more affordable. I will talk a little bit about, I have a couple of diagrams about that. 2 very good questions that are related to what I'm going to talk about. Yes.
You talk about the rule engine, right? So it seems like we had to explicitly know what we are doing. Sometimes we don't know what that attacker is doing. So do you think that sometimes we have to do some machine learning or AI in the rule engine? Or
Yeah, and I'm going to talk a little bit about AI as well. In general, so one thing that I told you the story about networks, and I told you that Falco has been inspired by network intrusion detection tools like Snort. So if you look at the Falco like rule, the Falco rule syntax is pretty similar to the Snort one. One thing about like when you were doing intrusion detection and runtime security using the network, you are far enough from the application that it's hard to express behavior, right? So your typical network intrusion detection tool has 65 million different rules with 1,000 coming every week. because you have to express these behaviors like, if a file with a specific signature was downloaded in an HTTP connection, you need to be very precise. When you can deal with stuff like system calls or logs coming from the cloud and so on, you can be much more behavioral. So I can express more like stuff like Redis container should only run Redis. In general, a container should only run what's put in the image of that container. So if somebody does a wget and then runs the file and then does a chmod and then runs that file, that's bad universally. I don't need a hash of that file to tell you it's bad and to very likely try to block it. So the fact that we are closer to the application and we're seeing executions, downloads, files, all of this kind of stuff allows us to. You still need a big set of rules, but allows you to be much more behavioral than what you used to do in the prior generation when you had signals like network packets that were less close to the actual action.
So is there a source for sort of recognized best practice for your Redis container where I can go and I can find a set of Falco rules?
Yeah, so Falco comes from comes with a set of rules. There are like 60 or 70 that are prepackaged with the tool and they're constantly essentially updated by the community. For every new release of Falco, you get it packaged with new rules. And there's also the concept of feed, so you can attach your Falcos to the community feed. And doing that, essentially, you get updates, like when whatever, there's maybe a new detection, new type of attack, and so on. So think about Falco as something that you have to manually, decide what you want to. You can do. It's very important for us that you have the ability and the freedom to do that. You don't have to, and the majority of the users don't do it. And the company that makes these laptops, for example, at their scale, they have people that are just writing Falco rules, because they use scale, they're specialized, and so on. But the average user, there's quite a bit of mileage that you can get with Falco out of the box. And if you want more, there are companies like SysDig, and we have a threat research team that creates Falco rules on a weekly basis and keeps you, always updated with all of the latest and greatest.
Referencing those against things like the MITRE attack framework?
Oh, absolutely. All of this framework, NIST, MITRE, all of this kind of stuff. And the rules are tagged. So when a rule triggers, you know that this rule is a violation of MITRE, and then you know exactly, what specifically it is.
Two questions. So the first one was some of what you've been saying earlier on reminded me of Think's Canary devices. And I'm not greatly familiar with the more Falco, so any at all similarity, or am I just making things up there?
Yeah, Canary devices like honeypots, that kind of stuff.
Well, Think's ones which of honeypots, but fancier, I think. I'm not too sure of the details.
So in general, it's quite a common use case for Falco. The idea, research team at SysDig runs a network of honeypots, just with the goal of detecting mobile cloud attacks. And what they do is they put machines on the cloud providers with not super tight security configurations, and then they have Falco running on top of it. Falco can tell you what's happening when it moves.
A question. Oh, sorry, carry on.
No, yeah. So these are use cases of Falco that are more than detection and response, are more like tentative.
The question was, you mentioned somebody Suricata, and so in the Sans Holiday Hack Challenge last year, playing on Suricata. So we're going to play around with Falco this year, or?
Hopefully, yeah. But Suricata is has been another big source of inspiration for us, just in terms of architecture and in terms of, and again, from that point of view, Falco really wants to be Suricata for cloud signals, and we see that as very complementary. So hopefully.
missing something. I don't know, get much, like when I saw the rules, looks like a C Linux things, you know, I see Linux.
Yeah.
Why actually it's like when you see the cameras, it's like, well, just seeing the cameras or just seeing the traffic instead of right away logging in.
Yeah.
In this case, I think you will need kind of an orchestration and automation response for that one that you have separated from what you do. So why not go to, like you say, these rails to do you on Rails, so don't let it do anything else. Instead of saying that we can monitor and see, I mean, allowing doing a lot more monitor than just not allow it.
So let me see if I understand the question. The question is, instead of doing detection, why just not blocking stuff?
Yeah.
Like the way SC Linux does.
Yeah.
Falco was born originally because I had many conversations of people that were like saying, the thing that I do when I deploy a machine, especially in the cloud, is I disable SC Linux because it blocks random stuff and it brings my infrastructure in a state that is fragile and it's essentially undebuggable. So the premise on top of which we've built Falco is Falco is a security camera. Linux is great if you want to use it, keep using it. There might be some use cases that overlap, but in general, Falco wants to be, let's say, a little bit broader than Linux. Linux is really focused on the Linux operating system and on certain detections. Falco wants to be a little bit broader, but in general, if you want to keep using SC Linux and put it for 0, you know, and do it. Falco is designed a little bit more on the philosophy of distributed system that collects signals and correlates signals from multiple machines and multiple sources. Is focused more on the security cameras, I was saying, and we base it on the assumption that response cloud is at a higher level, and normally what you can do is typically the response in the cloud is this container is misbehaving, let me kill it. And then you have an orchestrator, typically like Kubernetes, that will bring things back up. You leverage that essentially to keep, you know, things in a state that is consistent. Blocking a network connection for a web server because you think that the network connection is malicious, typically the web server is not equipped for a failure in an accept system call, you know? So what happens is normally that the web server goes in a state that's very hard to recover, and it's just very hard to understand what happened to that web server. So I don't want to say it's the only philosophy or it's the only right philosophy, but the philosophy that we adopt is more like kill stuff at a higher level and the whole pod instead of the specific action and let the orchestrator take care of the result in the pod. These, of course, has drawbacks potentially because there's a little bit of delay when you do that, right? While SC Linux is instantaneous and really blocks the.
Actually, you are the one who created it?
One of the original contributors. Creator is a big one. Yeah. One of the day one contributors to Varsha.
Wow.
And yeah.
Question about so it actually does system calls, and you're saying Falco also does that as well. So like how do you complement or like how do you defer as well for DPPS?
Let's go into instrumentation, okay? There was also a question related to this. So allow me to, in 10 or 15 minutes, just nerding out on one of the key data sources for SysDig, as I've mentioned multiple times, is system calls, right? So you need a way to to efficiently, transparently, and richly collect system calls on a Linux operating system, because Linux is the operating system that powers everything modern, right? You also want these to be core architectural thing that we had from the beginning. Is it needs to be container with the proper architecture. So we don't want to install something in every container. And of course, we want it to be integrated with Kubernetes. There are not too many options in Linux to do this kind of low-level system call by system call collection in through real time. Let's analyze this handful of options. First one is the so-called LD preload. Who's familiar with it? More than I thought. So LD preload is quite simple in concept. The technique name comes actually from the environment variable LD preload on Unix. You use to specify where the libraries going to be loaded from, right? So normally in Linux, the libraries are in /var/lib or wherever they are. But before running a program, you export this environment variable with the name directory. Then this program will go and get the libraries from this directory instead of the standard Linux libraries, or it will do it in this directory before going to the standard Linux libraries. So what you can do is, for example, if you're inside the container, you can start the container with this environment variable set, so that every process in the container is this environment variable set, and you point this environment variable to a mounted directory where you put libc, essentially. System calls are actually native operating system facility. No program. I mean, you can, if you want, write a program. It needs to be an assembly, essentially, to invoke a system call natively from your program. But every program on any types of program use libc to invoke the system call. So libc is essentially a library that has a one-on-one function for every system call and allows your application to call it. So if I replace libc with my own libc, I can put instrumentation inside it, and then I know essentially every system call that you do, and I can at that point build my data collection based on that. The advantages of doing it this way is that it's efficient because you're providing your own version, modified version of the library, and so you can really work and having it quite optimized. And conceptually, it's easy to implement. The problem with this is the long tail, right? Because you are replacing the library. So anything that you do wrong, anything that you do incompatible, the application is not expecting it, so it will crash. So it's pretty dirty, and it's a technique that is normally used, to create malware, or this kind of stuff. It's seen as, it doesn't have a very great reputation. The other problem is, I was saying, everything uses libc. Well, that's not the case anymore in cloud native, because there are languages, for example, Go is designed essentially to generate binaries that are self-contained and they don't have any dependencies. It's one of the architectural choices of the Golang language, So Go doesn't use libc dynamic libraries at all. So this technique is useless. So vendors or tools, open source tools that use this technique nowadays have huge blind spots. So this is something that was used a lot in 2015, 16, 17. Nowadays, there's still vendors that are using this, but if one of them, better to avoid. The second technique is retrace. Retrace is something that is not really at the library level. is the facility in the operating system kernel, in the Linux kernel, to do a bunch of really core stuff that you have to do when you're troubleshooting applications. Ptrace is how you set a breakpoint in Linux. Ptrace is how you inspect memory of a process typically. Ptrace is how you look at the register of the CPU. So Ptrace gives you a lot of power and a lot of control. Among other things, Trace also has a facility to intercept every single system call. It is and powerful. And in fact, that's why Ptrace, essentially Ptrace, GDB is a user interface on top of Ptrace, but also strace. You know, if anybody has ever used strace, it's based on Ptrace. The problem with Ptrace is that it's based on a pretty ancient architecture where every time there's a signal from the monitored application, there's Ptrace generates sort of an interrupt and does a context switch and invokes essentially the instrumenting application, which means that every single of action that Ptrace is intercepting generates a context switch, which is something slow, you know, in an operating system. It means that Ptrace is great, but it's not good to be used in production because when you instrument an application with Ptrace, you can expect a slowdown of probably 200x of that application.
Can I ask a question on that? Is there an amplification effect? Is it a one-on-one? So if for every system call from the app, is it a one or
Correct.
is it an amplification type scenario, 1 to 4?
It's one-on-one.
Okay, cool.
It's exactly one-on-one.
Okay.
So if your application is doing 1,000 system calls per second, you will actually have transition for 1,000 times a second.
Okay.
So it's of course proportional. The more I/O or system calls the instrumented application does, the slower. Yeah. Right. So let's go to way Falco does it. Falco uses kernel level instrumentation. So the idea is in the kernel of the operating system. It is very nice because you don't have to do anything on a container basis. Right? Both Ptrace and LD preload require you to go and instrument every single process, not even every single container, every single process in every single container independently. It's just a burden, you know, that way. Well, what the innovation that we brought with this thing with Falco is let's use the kernel of the operating system because every container shares the same kernel. That's the beauty of container. That's why containers are replacing virtual machines. With virtual machines, every single virtual machine has to carry its own kernel, its own operating system. That doesn't scale very well. The beauty of containers is that there's one kernel, and then the containers are just isolated computing environments that use facilities in the operating system, namely spaces and C groups, to make it look every container that is actually operating independently on its own machine. But in practice, all of these containers are sharing the same operating system. It creates an opportunity to go down in the operating system and intercept stuff there. And there's one point which is the system call interface where everybody needs to go. So you instrument one place and you see everything. This is a little bit like the packets never lie that I was saying before. Nowadays, I say system calls never lie. There's no way somebody will able to do something nasty and escape. You can escape LD preload because you can not call libc, you know, but you can never escape the kernel because if you need to do a network connection, you have to go through the kernel. There's no way for an application to do it. So you're always going through this. So now the question is, okay, the kernel is the right place to do this, is the best, the most efficient, the most powerful, and so on. How do we do it in the kernel? When we started SysDig, in early days of Falco, the technique that we used was kernel modules. A kernel module is the equivalent of a device driver, you know. So it's like a piece of code that you install. It's normally it's C code. You compile it, and it's a kernel module is essentially a library that is loaded by the kernel, you know. And it's good. It works. It's efficient. It's extremely efficient. But the problem of running software inside the kernel is yeah, you're increasing the disk and the attack surface. This kernel the kernel module could crash, and if it crashes, the operating system goes down. The kernel module could just have a loop, you know, and if it goes in a loop, have very likely like the deadlock or reliable kernel, and if in the best case you lose the CPU, and in the worst case you lose the whole machine. So eBPF, and how many of you know what eBPF is and how it works? And something like that. So let's do it. For these people, forgive me, I'm going to do just a little bit of a description. eBPF, the name is Extended Berkeley Packet Filter. Okay, so they took Berkeley Packet Filter originally is the piece of software that we put in the BSD kernel, and then I built a version for the Windows kernel that is a little virtual machine that at that point was used only for packet capture. So it was the facility that when you create a TCP dump or a wildshare filter, a port 80 is converted by a compiler into bytecode that gets injected through an IO control in the kernel of the operating system. The kernel of the operating system receives this, validates it. There's a validator. For example, you can originally eBPF did not allow you to do loops. Your code could only go forward, you know, so it was limited what you could do. But this guarantees that the code is 100% safe and will never crash and will never have a security vulnerability. After it's been validated, the program can be executed by the kernel. And originally, in the original BSD implementation, there was an interpreter for this code. I was the first one to write a just-in-time compiler, essentially, so the code could just be cheated in the kernel and would be, you know, as efficient as possible. I left it at that, you know. We used it as the core for Wireshark, for TCP dump, for all this kind of stuff. But the Linux community kept working on this, and they greatly improved it, gradually giving it more power, making the verifier much more flexible, so you could write more complex programs. So now loops are allowed, but only a certain number of loops, you know, and you can have code of a certain length, and you can now access some facilities in the kernel so you can get data in a safe way, but it's still completely validated. It's still completely safe. So you're guaranteed. And there's a powerful just-in-time compiler and all this kind of stuff. That's you know, and they converted something that was a packet filter into actually a very flexible and powerful virtual machine in the kernel. And originally, BPF, you could only do filters like port 80. Now you can write C programs. They are compiled, you know, by a compiler. They become intermediate bytecode. They go in the kernel and they are validated. So it's very complex, very powerful. But the result is that you have essentially a flexible computing environment in the kernel of the operating system that can run anything. You can write arbitrary code that is run safely, guaranteed to be safe inside the kernel of the operating system. Okay, that's eBPF. When we started working on our Falco instrumentation, probably the biggest eBPF program was lines of code. You know, people were using it to run little scripts in the kernel to maybe gather some information or do some profiling, look at filter network connections, and so on. We thought, okay, we believe it's possible to build a full-blown, essentially, system call capture architecture based on eBPF, but that's complex because you have the actual system call Inception, interpretation, you have to handle a circular buffer. You have to move the data as fast as possible, to the user level so that it can be interpreted and fetched. So it was quite an undertaking. And we built, like full-blown 10,000 lines of code set of eBPF programs that still now, like I tell you, this damn verifier, it's very picky, so you need to be very careful how you write this code, how many lines you have in every function. Once in a while, they modify something in the verifier and it doesn't work anymore. It doesn't work anymore. So very challenging, but we managed to write essentially full instrumentation written in eBPF, and that's how you use Falco normally today. And the eBPF implementation is fully on par in terms of functionality with the kernel module, and just slightly, just a little bit less efficient. It's still not like native compiled C code, but almost like that, because the just-in-time compiler is. There's a story of the kernel instrumentation.
Languages, when you say, imagine eBPF programs are very complex, and which is used.
Yeah, so it's the eBPF tool chain, compilation tool chain is based on CLang. Or in theory, you can use any language that CLang supports. 99.9% is C. So it's normally written in C.
How much of the actual processing of all the backend stuff happens in the program? So how much do you offload?
A good question. Philosophy here comes from packets, right? So my PhD is in high-speed packet capture, and essentially I worked for years on just taking an operating system kernel, work hard running inside this operating system, and make it as fast as possible at collecting and processing packets at 10 gigs, 40 gigs, and this kind of stuff, right? So what I learned during that process is don't try to be fancy. It's not the right place, The role of the kernel is in the data, shipping it out as fast as possible, because everything that you do in the kernel happens here, actually slows down whatever is running here. And so what I want to do is decouple as quickly as possible execution in context here with the actual processing that I'm doing of the data. What I mean is, if I actually evaluate the Falco rule here, not only it's slow, but it's also linearly slower in the number of rules that I have. Yeah. For example, Cilium has released a tool called Tetragon, which does something similar to what Falco does, but does it in place in the kernel. Every rule that you add, your application becomes slower, right? Because every new rule is more processing that is happening here, and this is in the this is blocking the application, because this happens while the system call is executed, right? So what we do is this needs to be, we measure the single clock cycle, and like cache hit for this kind of stuff, and this that what system call is executed, takes the relevant data for the system calls, moves it in a circular buffer. It's shared, memory mapped with Falco, the program. All of the computing happens here. This takes really only few cycles, so we're guaranteed not to slow everything down. And then, Falco uses CPU, but at this point you can control, you can limits to the Falco process if you don't want to use all of that CPU. What happens is you drop. So the drawback of our architecture is that if this is too slow, there's a buffer here, and you start dropping events. But we never slow down this. Advantage of an architecture like Tetragon one is it never drops anything at the cost of slowing down your application.
Potentially stopping that application.
Stopping. Yes. Yeah. Was the library one question here?
I'm just wondering about confidence level in stopping a couple of things is a bad thing happening. How can you reassure developers that just, Falco is stopping something, we have fairly high confidence level that it's legitimate.
As I was saying, Falco, this doesn't stop. This only collection and analysis, and the default deployment of Falco is detection only. Again, security camera. And that is one of the reasons for that is that there is no one-time security tool. There's no EDR tool that is guaranteed not to have false positives and false negatives. If somebody is trying to sell you something on the promise that they won't have, they won't make mistakes, they're lying to you, don't trust them. So the first thing is Falco is not perfect. There's noise, there's some stuff that is detected that is legitimate and is reported as potentially an attack, and there's something that can escape. So these tools are always need to be treated as a great supplement to security, posture, but not as the only thing. That said, Falco can also be used, as I was saying, with the response engines that kill stuff, block stuff, and so on. And in that case, there's a level of curation of the rules and correlation of the rules that we do. And the community does quite a bit of work with that, just curating and validating the rules. And want further essentially assurance. This is the biggest commercial product that does, among other things, exactly this.
So if we take the example of that company who makes those laptops, hundreds and hundreds of sensors, how do we aggregate? And I'm thinking data, must be a lot of volume of data to be processed. There must be intersects a little bit with Prometheus. Do we have a time series database deployments? And how do we do these correlations too? Because you mentioned a couple of times that you can correlate. So does that happen in Falco itself, or is there a third party, another piece of software that does correlations between the events?
Yeah, so Falco itself is in charge of collecting this data and generating the events on the data, essentially, based on rules that either come out of the box or that you provide. Falco Psychic is what sits near Falco and is in charge of taking this data and connecting this data with places where you can do something. Falco Psychic has many integrations, but as you can see, there are different categories. There's metrics. So essentially what happens is Falco emits events, but one thing that you can do is you can convert them to metrics. You can see every possible tool that is supported. And at that point, you can, like do volume analysis and the kind of stuff. There's a bunch of integrations with, this is outdated, by the way, there's many more, but a bunch of integration with logging tools. And then for these logging tools, we have schemas and this kind of stuff that you can use, and queries and dashboards that are prepared by the community, for example, for search or you name it. There's integrations with the function as a service frameworks, and this is more like for response. And this is when, like, do something when this specific Falco event is coming. And again, here the community is prepared, like recipes and things that you can deploy somewhat out of the box for that. And there's just, like reporting and alerting. So integration with Slack and all of these tools that you can use. Normally what the file that I described is more like the collection, and then you use Psychic to do essentially the specific integration that you might need.
Okay, thank you.
Yeah, it was just a technical question back on the packet filter and the syscalls. Completely get why you're not doing any rules processing in the kernel and you're sending that out to the user process. If you're logging all of the syscalls, every one of has got an overhead in terms of when it goes into the ring buffer and then the context switch when it comes out. For all those syscalls are like 99% of them signal, like 20% actually noise, or are there syscalls that you in practice nobody ever cares about, or is it actually most of them have got really good information?
Yeah, so what happens is you don't know a priori because it depends on what the user wants to see. And they use Falco offers a generic rule and rule language that you can use to specify whatever you want. You might want to detect, I don't know, accesses to a specific file name that is only relevant for you, you know, or you might need to look at a specific exotic system call. I don't know, in small, you know, to look if somebody is loading kernel modules into your operating system. So how do we decide which system calls to?
No, I'm not saying you should decide. I'm just interested. Like, for example, people, it's a bad example, but if a lot of programs called sleep very often.
No, yeah, exactly.
Sleep was never actually.
So
signal.
what happens is your rule set. You load your rule set here. Okay. Once you do that, Falco analyzes the rule set.
And it changes the packet filter.
Exactly. So it sees exactly which system calls you need for your specific rule set, creates the set, injects the set here. This creates a filter, and there's like a super quick hash-based filter for those system calls. So typically, one thing that we recommend when seeing Falco using too much CPU is go and tune the rule set for only the detections that you need. And likely, if you remove some of the rules that you don't need, it will use less CPU. Because there will not only it will use less CPU, but it will also drop less, because there will be less events that are captured and put in the share buffer. Okay. You do that, or you buy the commercial product from Sysdig.
I guess a shared buffer basically is like a copy of.
It copies elements of each system call that is useful to be able to run the rule set.
It's kind of running some sort of a regex to.
Yeah, of course, it cannot be a regex. Too slow, but conceptually it's a regex. Yes. Because maybe that one.
Alerts if any.
Absolutely, all of this information, as I was saying, there's quite a good enrichment that comes out of the box when a rule triggers. But let's take a look at the rule. It's easier to explain. So let's focus on this. This is a rule. This is an example of a Falco rule file where you can have macros and lists. These are just to help readability. You know, in a macro, I can give a name essentially to a subset of the field. And the list allows me to specify, like this is the term, I guess this is the terminal sharing container. No, bright binary deal. Okay. But the rule is name, description, condition. This is essentially a Wireshark filter on system calls. If you look at the syntax, it looks a lot like a TCP dump filter, right? So that's why I wanted to give you the history, you know. And then there's the output. The output is, again, a combination of fields. So Falco exposes unthreds and unthreds of fields. The system call name is a field, the file name, the directory is a field. So you use these fields in the condition to specify what you want. And again, these are system calls, but the fields don't need to necessarily be system calls. The field can be the Kubernetes label, for example, you know, or the namespace name, or it could be a cloud logging. So in general, you can use these fields in the condition, but you also use the fields in the output, right? So you can sort of fine. Of course, this come out of the box with already each set of information for every event, but you can decide if you want more information, what you put in the output. And this is, as you can see, flexible and it's field based. And so you can have the output as rich as you want. You know, this can include really information about the system call, about the process, about the file descriptor, so like the connection IP or the file name. It can be the Kubernetes, any kind of data, the Docker, the container name, the container image, the pod name, the cluster labels, whatever you want. So you can make it as fancy as you want. Essentially, you know, then Falco comes with like 100 plus of these already made for you, but otherwise you can make your own one. If you've used Wireshark or TCP dump, it will be very familiar.
Like the events you're producing, so it's like looks like there are multiple producers, but there's only single consumer. So it could be possibility that you can put multiple consumers also.
Yeah, there's full flexibility to do that. You could do that for several reasons. One is you actually want to isolate stuff, and you have maybe different, for example, domains or clusters or stuff. Absolutely no problem. Is whatever, performance. Maybe you have a lot of stuff and you don't want to centralize everything, but absolutely you have flexibility to do as you want.
I'm quite interested in, so you mentioned a couple of times about dropped events. So as an attacker, could you stop like a denial of service where I spam system calls?
So there's in general, again, let's do the honest premise first, which is will not stop a motivated, skilled attacker who wants to denial of service. That's true for every single security tool. You name it. Your CrowdStrikes, your whatever you want. If I'm motivated and I have access to the machine, I will toss all of them. There's no escape. In general, nonetheless, we try to have mitigations for this kind of stuff. We try to, for example, detect when somebody's clearly doing like a loop of calls, and we try to filter it out. We try to have detections that notify the user when something like that happens, to get an early sign and stuff like that. So it's not perfect, but there's a bunch of things that are embedded in the Falco engine to try to mitigate these problems as much as possible.
Is there any signal when something's dropped from you?
Yes. I think it's enabled by the frame. You will get a Falco event telling you something about an attack, tells you I was dropping. I started dropping.
The sort of basic security cases that you see Falco being used for.
So the system call rule set is a lot of behavioral stuff. Basic rules like a shell was started in a container, and there's much more sophisticated stuff like we have rules on recon. So we have a bunch of rules that detect when somebody is trying to the, I don't know, SSH directory, or trying to look for AWS credentials on the machine, or we have a bunch of stuff on creating remote shells. So, like using stuff like and Netcat to create shells. We have file system security. So every downloading stuff using wget, executing stuff, modifying system binaries, modifying the etc directory, reading sensitive files, reading files in etc. It's quite broad.
On the host or on the container?
On the host and on the container. Based on the architecture that I showed you before, this is in the kernel, so sees both the host and every single container.
So,
And the beauty is you don't need to instrument every single container. You get it. New container starts, this is already in the kernel and is able to detect all of these kind of stuff.
so just to fill maybe a gap here, you can use Falco on Linux host or on a Kubernetes cluster or a number of different things, and it will give you value. So because there are rules tagged to, for example, connecting to a crypto mining or using Stratum protocol, or there's a number of rules in the default rule base which are effective on Linux, on any Linux host, as well as being effective inside a container.
Exactly. The instrumentation is absolutely doesn't matter, and the rule set contains stuff that is container only, stuff that is for host only, and stuff that is for both.
A lot of instrumentation very much constrained on things like event and log rates, which can be very expensive, right? So it's Kiwi basically per gig to ingest logs. Provide an opportunity to reduce the cost to high quality settings.
Yeah, so and that is a little bit because this is more like what I was telling you before were the system call-based detections. In practice, Falco also be used for cloud log detections, you know, and in this case, essentially, same the example with the presentation, but you can write a rule with similar syntax, but to detect something like, I don't know, there was a login in my US region without two-factor authentication, or I don't know, a new bucket was created, or an instance of a certain type that is not allowed in my infrastructure was created, or all of this kind of stuff that are more like detection based on events that are coming from CloudTrail, Azure Log Analytics, Google Cloud Logging, Kubernetes, the logs coming from Kubernetes and so on. So the idea here is SIEM is important, collecting the data for forensics information is important, but there's a little bit of a dynamic similar to the system call one, you know? Do you really need to collect all of this stuff when you need to do detections? Very often for detection, you need to look at all of the signals that many times you throw away, you know? So the industry solution is drop everything with the maximum possible granularity into an XDR or a SIEM tool and so on, and queries on that. Well, there's two problems with that. Number one, it's always going to be late because you need to ingest these logs and then you need to run your queries on these logs. You cannot do a query every second on a login system. So you will do them every 30 minutes or something like that. So remember, attacks last seconds now, you know? So you're always late. The second thing is you're spending a gazillion amount of money for something that very likely you don't need, especially when your goal is granular detection, you know? So Falco wants to bring a perspective which is, instead of doing that, at least for many detections that are a little bit more, you know, basic and instantaneous, you can just take your logs, them to Falco. Falco emits alerts, and then maybe these can go to the SIEM. So Falco has two advantages at this point. One is it can detect it and notify instantly, so there's no delay. It's very simple, lightweight, and cheap to deploy, and can act as potentially a filter, you know, for the data that is going to the SIEM, and can greatly reduce the data that is going to the SIEM.
Alert can just be JSON going ingesting into it.
Exactly.
Okay, so how this rules will implement with something like
policies or guardrails? Because like you said,
Policies or guidelines you mean like policies like
so it's like one of the examples is if there's instance being created in regions that are not approved.
yeah.
We can
Policies like posture policies, for example, is that what you're
or like
talking
a,
about?
like
Like CSPM, for example. We see this as very complementary. In fact, this is a little bit more like a topic of our commercial product, maybe like of Falco. Falco focuses more on the detection side, but Sysdig Secure, which is our commercial product, has a bunch of functionality to tie the two things together, and make it possible, for example, to use alerts as a way to validate policies and then potentially provide feedback so that the policies can be modified in case they trigger something a million times with Falco because maybe they are too tight and so on. So the Secure, the commercial product, has both a policy side and also an infrastructure, a code side that can be used essentially to on the fly validate these policies, and also the runtime side which feeds into that.
I'm spinning up a Kubernetes cluster. Do I just need to start up a Falco container and give it extra privileges so it can write to the packet filter? Or
so if you're deploying Falco in a Kubernetes cluster, normally you would use the Helm chart for Falco. And if you don't use the Helm chart, essentially you deploy Falco as a daemon set. We are working on an operator which will essentially operate Falco fleet. Essentially, you need one Falco per machine. Plus, if you need the logs and the kind of stuff. But it's the operator that we're building will take care of all this kind of stuff automatically. Essentially out of time.
So what are there any additional limitations? For instance, in GKE, you have Autopilot, which has all sorts of restrictions that can run on Kube. On the Docker side, you have Podman that's running rootless. Are these type of sort of constraints limiting what we can do?
I mean, Falco's been around for a while, so all of this kind of stuff like Podman is supported. Typically, you should expect, you should expect to be able to throw arbitrary Kubernetes setups and configurations at Falco, and you should expect it to work. The limitation of Falco is currently is a open source version does not support, or at least there is support, but it's not really like supported by the maintainers for serverless containers. The reason there is that there's no access to the kernel of the operating system, right? So you cannot use the eBPF technique that I was talking about.
Lambda is generating CloudTrail events.
Yeah, I mean, the CloudTrails is not a problem, and use those. Cloud providers are quickly moving to start supporting eBPF for their serverless fleets, so we expect this to change. Again, for this Sysdig as a commercial solution, based on another further different type of instrumentation that we've created for that. Otherwise, like Podman.
Let's take example here. So when you're sending the CloudTrail logs to, the Falco, so is it going outside of the AWS or like are we running the virtual machine process this?
That depends on how you deploy it, because essentially what happens is you have a Falco engine, you receive these logs, and there are different deployment options that you have for that. One is like in place, so you can have Falco as close as possible to your log generating infrastructure and run it, for example, in a container or in an instance in place, or you can decide to have this engine somewhere else, even outside, like the cloud, and maybe you want to do it because you want to centralize your collection and kind of stuff. So again, for that you have flexibility, because Falco is just an engine that you can really choose where you deploy it.
So it can be like serverless Falcon also.
Yeah, the side, yes. Yeah.
Is there any more questions? Anyone have any more questions?
Plenty more.
Plenty more. So if you just drop it, Loris, can you just drop to the slide right at the end? We realize that cloud native security is quite a complex topic. It moves really quickly, and there's really a lack of, I guess, education and knowledge in this area. So what we've actually done is we've put together a few workshops that you may be interested in. One is what we call the Falco Up and Running workshop, and this is actually part of the Falco community. So this is part of the open source Falco community. There's an Up and Running workshop, which is mostly based around the open source Falco and the threat detection and those kind of things. But what we also do on the Kubernetes side is we have a workshop which we call Securing Kubernetes with Sysdig. So this does sit on the commercial side of the product. The commercial side of the product is much richer in terms of its ability to secure the entire software development lifecycle, all the way from infrastructure as code all the way through to runtime, including vulnerability management, posture, and entitlement management and compliance. It's much wider in the scope that it deals with. Both of these workshops are really educational, and feel free to, these are just expressions of interest. So if you are interested in learning more, either about open source Falco from a runtime threat detection perspective, or even if you're interested in learning more around the wider CNAPP category, Cloud Native Application Protection Platform, if either of those things are of interest, please feel free to, swipe or take a shot of the QR code and register your interest. We are looking for expressions of interest because we are running workshops. We're trying to get a gauge of where people are interested in the workshop so we know where to run them. So feel free to register your interest, and what we will do is we ask for your email address, and once we know where there are people interested, then we will put on a workshop where there is interest in the workshop. So that's a good place to go next. But there's also Falco community, falco.org is the Falco website. There's a really good Slack channel on Kubernetes under the hashtag Slack. It's under Falco, hashtag Falco under the community Kubernetes workspace. And there's probably 2,500 people on there that talk regularly about Falco stuff. But there's a big Falco, the Falco community. There's people around the community who use Falco, and we're working to build that community inside New Zealand so that we can all work together and, make cloud and cloud native safer. But yeah, feel free to connect with us if you want to. Feel free to register for a workshop. We're happy to help. But yeah. Thanks for coming, everyone. Appreciate it.
Other than that, thank you very much for attending.
Thank you.
I just say thank you to Loris for your work on Wireshark, because it saved my ass on a number of. Stops DDoS attacks as well.
Use Wireshark every day.
Yeah, it's still downloaded like 500,000 times a month, it's crazy.